Good afternoon, sir.
Good afternoon, sir.
Good afternoon, sir.
Hello. Okay, class. Before we start, just tell me one thing. That last time on Friday, uh, during the end of my class, who pointed it out that Z bar is does not have a primitive? Who pointed it out?
Yes, sir. Ashish.
You, Ashish.
Yes, yes.
Anyway, thank you, Ashish. Actually, when you asked me that, you pointed out that that Z bar is sir is does not have primitive, perhaps. So it immediately struck to my mind. Perhaps that confusion crept into due to the way I was deliberating upon the things. So it immediately struck to me that, oh, in my deliberation, perhaps the confusion is because of this reason. So then I think by the evening on that very day, I emailed a note to all of you on Google Classroom. So Ashish, now I think you must be satisfied.
Yes, sir. Yes, sir.
Yeah, yeah. So I'm sorry, and thank you very much to you. I really appreciate it that you were very attentive and you brought that into notice. Yeah, sometimes it so happens because just in the beginning, as I told you that we can broadly categorize the complex valued functions in two parts or in two types, namely one where the complex valued function is just a function of real parameter, and then the life is very simple and the things more or less go as we do with the function with the real valued functions. But secondly, when the complex valued function is of general nature, then it means when it is exactly the function of complex variable z, sometimes exclusively, sometimes not exclusively. So then of course the things change, and it is exactly uh, it is exactly uh, uh, where we feel a difference between the discussion of real valued functions and complex valued function. So once again, Ashish, thank you very much for bringing that into my notice. So with these words, let's start with the section 2 of chapter 4. Okay, so I'm going to share the screen. Class, can you see the screen?
Yes, sir.
Okay.
Yes, sir.
So first of all, let me give you a brief account of what we shall be doing in this section. What happened? Okay, class. So let me tell you that in this section we shall be learning the following three things. Number one, for every analytic function, we can write a power series. Of course, precisely uh, so far as the information about the domain of the analytic function is concerned, where the power series will be convergent. All that, of course, I shall be mentioning while doing the precise result. But the crux of the matter is this. So we shall be learning this, that for every analytic function, we can write a power series. Secondly, every analytic function, or you can write, if you don't want to write every, you can write n for n. N means, sorry, n means any arbitrary. An analytic function is infinitely differentiable. Of course, wherever the things are meaningful. And thirdly, what we shall be learning the following in this section, that along a closed rectifiable curve, the integral of an analytic function. So as you can see, our prime focus in this section will be nothing but the analytic functions of an analytic function vanishes. Vanishes means is zero. Okay, class. So I am going to start with the following, what is called as the Leibniz rule. I'm going to start with this. Leibniz rule. And basically, this is a result which is some sort of differentiation under the integral sign kind of result. So the first of all, I'm going to write the statement of the result. This rule says that phi from closed interval AB cross C comma D. So as you can see that this is nothing but a geometrically, this is nothing but a geometrically, this is nothing but a rectangle in xy plane. Uh, so let phi be a function going from here into C, and suppose it is continuous. Let G be a function which is defined on closed interval CD. Take a note, this CD is same as this CD. Because please take a note that whenever we take same notation in one particular discussion, then we don't have any reason to make any distinction between those two notations. So they will read the same meaning always. So this, and we are defining from here into C. Let this be defined by, and we are defining this function like AB phi of s comma t ds, where, yeah, it's okay, that's it. As you can see here that g is a function of variable t, because class, take a note that here you are taking integration with respect to the variable s, and because the limits of integration, they are fixed, so it means ultimately when you compute it, this overall expression will come out to be what, nothing but a function of
T.
yeah, t, correct. So we have phi, a continuous function, defined on a rectangle in R2. It's a continuous and complex valued. We have G, a complex valued function defined with the help of this integral. Then class Leibniz rule says that then number one, G is continuous on closed interval C comma D. And secondly, it says that if, so we are assuming this additional condition. So if partial derivative of phi with respect to t exists, and not only this, exists and is continuous. Moreover, it is continuous. So please take a note. When you take this derivative, let us say this will be a new function. Let us call it phi naught s comma t. So please take a note that this function will also be defined from a comma b cross c comma d to c. So this function, this partial derivative exists and is continuous. So certainly this will be continuous on class this rectangle. I'm saying this continuous. Then this point number 2 says that then point number A, G is continuously differentiable, continuously differentiable. Class, in fact, there is no need to say this on CD because this is understood because G is defined on CD. So this is understood that we are talking of continuity of G where. So this is understood. But if you want to write, you can write for the sake of clarity on, because I don't want any confusion on C comma D. And likewise, it is continuously differentiable on again C comma D certainly. And class, you know the meaning of continuously differentiable. Continuously differentiable means class that derivative of G will exist, and moreover, the derivative will come out to be a continuous function. Right, class?
Yes, sir.
Yes, sir.
B. So G is continuously differentiable. And secondly, what will be the derivative of G? The derivative of G, I am talking of the derivative of G. And secondly, the derivative of G will come out to be this integral a to b yes. Of course, it's an understood class that you will get this for all t in closed interval c comma d. And this will be the derivative of G. So class, basically this is differentiation under the integral sign. We have differentiated G. If you have a close look at this expression, then it means basically what we have done. We have taken the derivative of G with respect to t, right class? So it means we have taken the derivative of this integral. Is this okay, class? And basically we are showing now, or we will be showing in this part B, that actually this is nothing but you simply take the partial derivative of integrand with respect to. So this is class differentiation under integral sign. Is this okay, class?
Yes, sir.
Yes, sir.
Yeah. So class, this is Leibniz rule. We are given a phi, we are given a G, defined like this. We are to show that G is continuous. Further, if the integrand has partial derivative with respect to t, and moreover that is continuous, then G itself will also come out to be continuously differentiable, and moreover the derivative of G will be this. So let's see the proof of this result, class. It's a nice result. And next, we will be seeing a beautiful application where we shall be computing an integral. So class, before I start proof, You remember the following. You remember. Remember the following things. Point number one. A subspace of real line endowed with usual metric is compact if and only if subspace you can say S. If and only if S is class S is
Closed and bounded.
Closed and bounded.
so you remember this. Number two, you remember the following. Product of two compact sets is a compact set. You remember this. And thirdly, you remember this. Continuous map, a continuous map defined on a compact set is what class? Is
Compact.
oh, read the sentence carefully. A continuous map defined on a compact set is
Continuous.
Different.
oh, Bhagwan. Who will tell me?
Mm.
Is who will tell me?
Bounded, sir.
Oh my God.
Bounded.
Actually, that is the beauty of compact sets. One of the big advantages of studying continuous map on compact sets is that class. Every continuous map is
Connected, sir.
Website.
no,
Uniformly continuous.
yes, is uniformly continuous. That's the main thing. Is uniform continuous. Plus, uniform continuous maps are very strong. And the one of the very strong implications of uniformly continuous maps is that they map Cauchy sequences onto Cauchy sequences. If a map is continuous, that need not map a Cauchy sequence onto a Cauchy sequence. But if it is uniformly continuous, it will take Cauchy sequence to Cauchy sequence. It means the image of a Cauchy sequence under a uniformly continuous map will also be Cauchy sequence. And that's something very important. Anyways, so class, you remember these three things. I shall be making use of these 3 points. Okay. Now, so now we will first of all do the first part. To show what class? To show that G is continuous on uh, closed interval C comma D. Right class? This is our first part. Right class?
Yes, sir.
So let T be an arbitrary point in C comma D. So class, I will simply show that G is continuous at T naught. Is this okay, class?
Yes, sir.
G is continuous at T naught. I will show this. And because T naught is an arbitrary point, so that will automatically imply that G is continuous on closed interval CD. Now, class, you recall the definition of continuity of a function at some point. For this class, what we will do? We will take some epsilon greater than 0. Let this be given. Class, actually, this is just, I must say, the language. Let epsilon greater than 0 be given. It actually means that whatever epsilon bigger than 0 arbitrary you take, very, very often quite close to 0. Then class, you just recall the definition of continuity. It means we will have to show the existence of some delta that will depend upon T naught and epsilon. So we are such that class, whenever mod of T minus T naught is less than delta, right class, because we are in real line with usual metric, that's why distance between T and T naught we will find out with the help of modulus. So whenever for all those sorry, थोड़ा जगह ज़्यादा बना लेता हूँ. So for all those T which satisfy this condition class, the images of such T's under G must satisfy what?
Epsilon.
Epsilon. This is the definition of continuity of a function at a point T naught. Is this okay, class?
Yes,
Yes,
sir.
sir.
And I
Yes,
will,
sir.
and I will show you this. So, and this you have been doing since the first year of your college days. So let's start now. Clearly, this and this are compact subsets of R. Is this okay, class?
Yes, sir.
Because they are
Yes,
closed,
sir.
because they are closed and bounded. Is this okay, class? Of course, this needless to say that we are working with usual metric. There is no need to write it again and again, class. Is this okay, class? In our
Yes, sir.
whole course, we shall always be using only the usual metric, whether it is R, whether we are taking the elements from real line, taking the elements from complex plane, taking the elements from R2. Always we shall be considering the usual metric only. Clearly this implies this is compact subset of R2. Is this okay, class?
Yes, sir.
The product of two compact sets is compact. Is this okay?
Yes, sir.
Now, phi being given continuous on this, so it is, yes,
Uniformly
uniformly
continuous.
continuous. Got it. इज दिस ओके क्लास? तो मैंने जो रिमेंबर में तीनों पॉइंट लिखवाए थे वो तीनों पॉइंट मैंने यूज कर लिए. इज दिस ओके क्लास? ठीक है क्लास? Now we will use the definition of uniformly continuous. Now because phi is uniformly continuous, class, this implies that. So class, what is our aim? Our aim is, for this epsilon, our aim is to find out a delta. We are to show the existence of this delta, for which whenever you take any t satisfying this condition, we should have this condition. So our intention is to find out that or to locate this delta. So let's see where from we get this delta. Is this okay, class? Now, because phi is uniformly continuous, So by the definition of uniform continuity, for a given epsilon greater than 0, there must exist a delta which depends on epsilon only. Please take a note, class. In the case of uniform continuity, delta does not depend upon the points. Right, class?
Yes, sir.
Greater than
Yes,
0.
sir.
Of course, this is
Yes,
understood.
sir.
Greater than 0. Such that, recall the definition of uniform continuity, class. Such that distance between, I am taking 2 points, S1 comma T1 1 point and S2 comma T2 another point, that this distance will be less than
Epsilon.
whenever, yes, you are right, epsilon, or class, by now you know I can take some multiple of epsilon, so I am taking this. Is this okay? Epsilon or some multiple of epsilon. Is this okay, class? So whenever the distance between these points, they are the points of R2, is less than delta. Is this okay, class? So actually, I'm going to tell you, it is this delta which we are getting from the uniform continuity of phi, which will serve our purpose. Is this okay, class? Is this okay, class?
Yes, sir.
Now, in particular, if we take, what we do, class, we take S1 is equal to S2 is equal to S. Yeah, it means we are taking S1 is equal to S2 and we are calling their common value as S, and we are taking T1 is equal to T and T2 is equal to T naught. Then the above gives what it gives, class? It gives phi of, sorry, it gives very easy, phi of S comma T minus phi of S comma T naught will be less than epsilon upon P minus A plus 1 whenever, what do we have, class? Whenever S comma T minus S comma T naught, a modulus is less than delta. Is this okay, class?
Yes, sir.
But class, have a look at this. What is this, class? This is nothing but the usual distance between two elements of R2. So what is this, class? This is under root of S minus S square plus T minus T naught square. Is this okay, class?
Yes, sir.
This becomes 0. And when you take square root of this square, so this will ultimately be modulus of T minus T naught. Is this okay, class?
Yes, sir.
Is this okay, class? So basically, I am saying whenever modulus of T minus T naught is less than delta. Is this okay, class? Is this okay, class?
Yes, sir.
Yes, sir.
Yes.
Okay. Simple. So class, let me call it, let us say 1. So therefore, class, now we start with our goal, GT minus GT naught. We want to show that this difference is less than epsilon, right, class? Whenever mod of T minus T naught is less than delta. This is our aim, to show the continuity of G at T naught, right, class?
Yes, sir.
Yes.
Yes, sir.
So we start with this. So this is modulus of, and now class, you simply put the value of GT, which is, if you recall, is nothing but this, minus A to B phi S, and the value of GT naught will be, here you will have T naught. Is this okay, class? I have simply used the definition of G.
Yes, sir.
Yes,
Is
sir.
this okay, class?
Yes, sir.
Okay, very simple. And now this is A to B, it's a modulus, and you have phi of s comma t minus phi of s comma t naught ds. Because we had the same limits for integration, so I have combined both the integrands. And class, now I hope you can understand that this is less than equal to, you can take modulus inside, right class?
Yes, sir.
And now class, using 1, what do we have? This is less than equal to a to b. This thing is less than epsilon upon b minus a plus 1 for all those t which satisfy the condition that t minus t naught is less than delta. Is this okay, class? So I have used 1. Is this okay, class? Is this okay, class?
Yes, sir.
Is this okay?
Yes, sir.
Now this is equal to, you can take this outside the integral sign and into, and the integral will be a to b ds, and that will be nothing but class what? This is. And this is, if you notice, class, this denominator is bigger than this numerator. So this is further less than epsilon, I can say, because this thing is smaller than 1. Is this okay, class? And this is
Yes,
for
sir.
all those t which are satisfying this condition. So class, what I have shown you, that is, I have shown you the following. That is, I have shown you that modulus of gt minus gt naught is less than epsilon for all those t, or whenever t satisfies this condition. And hence done, class. This implies that g is continuous at t naught, and hence, and t naught was arbitrary, and hence it is continuous on c comma t. Is this okay, class? Very
Yes,
nice
sir.
proof. Very nice. Very easy to understand. Now let's take up the second part. What's the second part? In second part, we are given the information that the partial derivative of phi with respect to t exists and is continuous. So we are to show that g is continuously differentiable, and the derivative of g is coming out to be this. So g is continuously differentiable means, class, to show this, we need to show two things. Firstly, that g dash exists, and secondly, class, g dash is
Continuous function.
continuous function. We need to show we need to show two things, and when we move on to show that g dash exists, we will see that g dash exists, and moreover the value of g dash comes out to be this. So our part b will also be done automatically. So let's see how do we proceed. Okay. So class, first of all, I will show g dash exists. I will show that g dash exists, and its derivative is this. And then I will just establish this in one line, that g dash is continuous as well. Now to show that g dash exists, class, what I will do, let us take t naught to be an arbitrary point in this. So class, I will simply claim that g dash at t naught exists, and the value of g dash at t naught is what class? A to b this. And because class t naught is arbitrary, so it means the claim will hold automatically for all the elements of closed interval CD. Is this okay, class?
Yes, sir.
Right? Now, class, to show that g dash t naught exists, I need to show that class limit t tending to t naught. You recall the definition of derivative of a function of real variable. If you recall, this was the definition. If this limit exists, then we say that the function g is differentiable at t naught, and whatever the value of this limit comes out to be, that will be, or that will give us the value of the derivative of function g at t naught. Is this okay, class?
Yes, sir.
So I want to show that this limit exists, and moreover I want to show that the value of this limit will be class what? A to b del phi by del t s comma t naught and ds. And moreover I want to show that the value of this limit is this. Isn't it, class? This is exactly what I want to show. Is this okay, class?
Yes, sir.
And now you recall the definition of limit. According to the definition of limit, it means let epsilon be greater than 0. Let epsilon greater than 0 be given. Let me call it number 2. So class, if I want to show number 2, then it means what? It means, class, if you recall the definition of the limit, this is just nothing but, class, just a function. It is just a function. And it is nothing but the value of limit of this function. So if you want to show that the limit of this function is coming out to be equal to this right hand side of expression number 2, then it means, class, what? It means we want to show that then our aim is to show that here exists some delta which depends upon t naught and the epsilon, such that, so we are to show the existence of this delta such that, class, whenever mod of t minus t naught is less than delta, we should have the difference of this function with this limiting value to be less than what, class?
Silence.
Epsilon. क्यों, क्लास? यही तो डेफिनेशन होती है लिमिट की, ठीक है ना?
Yes, sir.
तो एमएससी में आ गए हैं तो बेसिक कॉन्सेप्ट थोड़े ना चेंज हो जाएंगे. G is just a function of a real variable. Definition तो वही रहेगी. Okay, good enough. Good enough. Just a minute, class. So let me call it number 2. Let me call it number 2. So class, now finally, to show 2, I need to compute this expression separately. So we shall be computing this expression separately. So now our next step is to compute This is our next step. And class, this is perhaps the most important part of the proof of this part. See how I'm proceeding now. First of all, note that using the explanation same as above done for phi, we have that for phi 2. Now class, take a note. If you notice, class, if you notice in the definition of G, then this phi is the integrand. And I showed you while proving this first part that phi, uh, sorry, that phi is uniformly continuous. Using this fact, we established this relation, class. Now class, take a note that instead of phi, if I use phi naught, then we know that phi naught is also given to be continuous on this. So similarly, I can say that phi naught is uniformly continuous on this. And a similar information I can write about phi naught also. Exactly this kind of information, right class? In fact, I am talking of number one. I can write this number one for phi naught also, class. Is this okay? Because phi naught is also having the same properties as phi is having. Is this okay, class? Is this okay, class? It is given to us, na? It is given to us that phi naught is continuous. It is given. If it is given, na, that phi naught exists and is phi naught is continuous. And if it is continuous on this, then certainly it is uniformly continuous. And certainly for phi naught also, I can write number one. Is this okay, class?
Yes, sir.
Yes, sir.
Okay, fine, good enough. So for sorry, it's not phi 2, sorry, it's phi naught. We have that there exists a delta which depends upon epsilon, which depends upon T naught, such that class modulus of phi naught s comma t minus s comma t naught is less than epsilon upon b minus a plus 1 whenever, you can write whenever or you can write for all t which satisfy this condition. So if you allow me, let me call it 1 dash. So 1 was for phi and 1 dash is for phi naught, because we had the same information about phi naught as it was with the phi. Is this okay, class? Is this okay, class?
Yes, sir.
Okay,
Yes,
now,
sir.
now thus for those t which satisfy this condition and those s which are in closed interval AB, we have the following class: modulus of t naught to t phi naught s comma u minus phi 2, sorry, sorry, I am writing phi 2 again, s comma t naught, sorry class, du. Class, take a note that here instead of variable t, I have taken u. Reason being is that I have used the notation for t here in the upper limit. So I am integrating it with respect to u now. Or you could take some other notation, whatever suits you. So class, this is less than equal to integral t naught to t modulus of f naught s comma u minus phi naught s comma t naught du. And now class, take a note. Can someone of you tell me that, okay, if you notice u is varying in between t naught and t, isn't it class? Isn't it class?
Yes, sir.
Yes.
So suppose t is here, t naught is here, so u is somewhere here. This is u, this is t naught, this is t. So class, this is very obvious that distance between u and t naught will certainly be less than equal to distance between t and t naught. Is this clear class?
Yes, sir.
Is
Yes,
it
sir.
okay class? So it means, class, it means distance between this u and this t naught is less than equal to distance between t and t naught. So it means, and which is further less than delta. So it means distance between u and t naught is less than delta. And if distance between u and t naught is less than delta, for u and t naught I can apply 1 dash. Because take a note, you can apply 1 dash only for those points t such that t and t naught is less than delta. Now I am seeing that distance between u and t naught is also coming out to be less than delta. So I can apply 1 dash. So this is further less than equal to. So now I can apply 1 dash. It means t naught to t, and this is b minus a plus 1 d. Is this okay, class? Is this okay, class?
Yes, sir.
Yes,
And
yes.
is this okay?
Yes, sir.
And this is further less than, class. Simply epsilon upon b minus a plus 1 modulus of t minus t naught. Sorry. Modulus of t minus t naught. Actually, you will get t minus t naught, but because t is bigger than t naught, I have put the modulus. That hardly matters. So class, let me call it number 2. Now class, see, let us, if you notice class, you can take this expression as function of u, because here u is the only variable. S and t naught, they are fixed. You can see here that only u is changing. So let us say that this is fu. And now class, what I am going to do is, I am going to find out a primitive for this fu. Now, what I am going to do, we shall now find the, or locate the primitive for fu. This is, I am writing just to explain you, just to make you understand that what I am going to do now. In class, you can see that if we consider for S is of course in the interval a comma b, this consider this function capital F. This is a function of variable u, and defined on this f is this u is coming from closed interval CD. Take a note here, this u is coming from, it is the second coordinate, so certainly it is coming from closed interval CD. Is this okay, class? So consider a function capital F u defined like this: phi s comma u. So here your variable enters, minus u, again your variable enters, phi naught s comma t naught. Class, then class, can you tell me what will be the derivative of f with respect to u? Take a note that s and t naught, they are not variables. S once chosen in closed interval AB is fixed for our discussion now. So class, what will be f dash u? You simply take the partial derivative of phi with respect to u. That is nothing
Yes,
but phi naught. Is this okay?
yes, sir.
Minus, and now this is fixed. So,
Fine.
yeah, it will be the derivative of u will be 1. So you will be left with this constant kind of thing only. Is this okay?
Yes, sir.
Yes, sir.
And if you notice, this is nothing but what? Isn't it fu? Is this okay?
Yes, sir.
So I have been able to find out a primitive for small f. So therefore, class, therefore from 2, therefore, sorry, therefore from 2 we have, so class C. So now I am going to replace this with what? I'm going to replace this with f dash u. Is this okay, class?
Yes, sir.
So from 2 we have modulus of t naught to t f dash u du, it was less than t minus t naught epsilon divided by b minus a plus 1. So we have this thing was less than equal to this. Is this okay, class? Is this okay, class? So from 2 we have this now. And you know that, class, this implies if f dash is the primitive, class, then the value of this integral will be what? The value of f at t minus the value of f at t naught. Is this okay, class? It means this is less than. Is this okay?
Yes, sir.
Now put the value of ft. What was capital Fu? Capital Fu was this. So what will be ft? You put u is equal to t. And likewise ft naught. For u, you put t naught. So I am going to do that. So, or, so by using the definition of capital F, it will be what, class? Y s comma t minus t phi naught s comma t naught minus phi s comma t naught minus t naught phi naught s comma t naught this. So this is less than. So I have simply used the definition of capital F. And class, if you simplify it, you will see that uh, this will come out to be uh, this will come out to be, or you can see that this will come out to
हाँ
be phi
ठीक है
s comma t minus phi s comma t naught, and class minus, you will see that t minus t naught will be common, and you will have phi naught s comma t. This is simple algebra. You can check it. You will have this thing. You just combine all these terms, all these four terms. Is less than epsilon upon b minus a plus 1 modulus of t minus t naught. And now class, what I can do is that I can take t minus t naught common. So if you take t minus t naught common, so you will have this minus this divided by t minus t naught minus phi naught s comma t naught modulus, and you are taking t minus t naught common, less than epsilon upon b minus a plus 1 t minus t. Simple algebra. So class, these two will cancel out each other because t is not equal to t naught. That is understood. We are taking t to t naught, right? We shall be approaching t to t naught. T is not equal to t naught. Is this okay, class?
Yes, sir.
Right? So let me call it number 3. So now class, uh, we are almost done. What was our intention? Our intention was to compute this. So now I am going to compute this, class. All this exercise I have done to compute this expression. See how. So now, yeah, therefore, I can say that gt minus gt naught divided by t minus t naught, this is equal to 1 upon t minus t naught. And let us put the value of gt, class. This is how gt is defined. It is already given to us. And this is equal to, if you see, it is nothing but a to b finally, class, because the limits of integration are same, so you can combine the integrands and divided by, because uh, this thing which is outside the integral sign is independent of the variable of integration, so you can take it inside, class, inside the integral sign. Is this okay, class? Is this okay?
Yes, sir.
So let me call it number 4. And now let us start computing this. And finally, we will show, class, that this is coming out to be less than epsilon. Is this okay, class? Is this okay?
Yes, sir.
Whenever we have this has already come into picture, class. It is this delta which will serve our purpose. So now let us start computing with the left hand side of 2. Our intention was to establish 2. So therefore, hence finally we have this modulus of gt minus gt naught divided by t minus t naught minus, hence starting, मैं लिख भी देता हूँ right here, with the left hand side of 2. We wanted to establish 2, so we are now finally starting with the left hand side of 2, having done so much of homework. Phi naught s comma t naught ds. So this is nothing but, class, what? Del phi by del t at s comma t naught. Is this okay, class? So this is equal to, now you use 4. From 4 we can put the value of this expression. So it is integral a to b phi s comma t minus phi s comma t naught divided by t minus t naught minus integral a to b phi naught s comma t naught ds. Is this okay, class? We have used 4. Is this okay?
Yes, sir.
Is this okay, class? In class, because the limits of integration are same, we can combine their mm, integrands, and we can take modular sign inside, so it will be finally less than equal to a to b modulus of phi s comma t minus phi s comma t naught divided by t minus t naught minus integral a, sorry, minus phi naught s comma t naught, its modulus and ds. Is this okay, class? And now, if we use 3, class, you can see that this difference is less than this number for all those t for which mod of t minus t naught is less than delta. Is this okay, class? So using 3 now, this is, class, less than epsilon upon b minus a plus 1. So I can take it outside the integral sign, a to b ds, using 3. Is this okay, class?
Yes, sir.
Yes,
And
sir.
and class, this is, please take a note, 3 was true only for those t's which were satisfying this condition, if you recall, right? And class, this is epsilon upon b minus a plus 1, and when you integrate it, you will have b minus 1, and because this thing is less than 1, class, so the whole thing will finally be less than epsilon. And of course, all this is there. This is here as well. So class, that is what we have shown. That is, class, we have shown that corresponding to the epsilon greater than 0, which the which we took in the beginning, we are able to show the existence of a delta. This delta we got using the uniform continuity of phi naught, right? So we are able to get a delta such that, class, this difference such that this difference sorry, such that this difference is coming out to be less than epsilon for all those t which satisfy this condition. Is this okay, class? Is this okay, class?
Yes, sir.
And class, this means what? This means that limit gt of this is nothing but the definition of limit. It means, class, this limit exists. It means, class, this limit exists, and its value is what, class? A to b phi naught s comma t naught. Is this okay, class? And what is this, class? This is nothing but
G dash
g
T.
dash at t naught. Is this okay? And class, if you recall, this phi naught was nothing but this, right, class?
Yes, sir.
And because since t naught in the interval cd was arbitrary, this was arbitrary, na, class? It
Yes, sir.
follows
Yes,
that
sir.
g dash t exists for all t in closed intervals c comma t, and moreover, G dash T is equal to A to B del phi upon del T S comma T ds for all T in closed interval C comma D. It means now I can say this for every element of closed interval CB. Is this okay, class? Is
Yes,
this
sir.
okay, class? And,
Yes, sir.
and now, class, using first part, if you recall first part, and just now by lastly by part 1, lastly by part 1. Now, class, what you do in part 1, instead of phi, you consider pi naught. Is this okay? And for example, you called G dash to be some H. So class, part 1 says what? That E and phi naught is given to be continuous to you. So part 1 says what? That if you have a function ht of this type where phi naught is continuous, then h will be continuous. This was part 1, if you recall. See, what was part 1? See, uh, this was part 1. If you have a continuous function here and g is defined like this, then g is continuous. So instead of phi, you take phi naught. You replace this phi by phi naught, and instead of g, you have g dash. Call that h. So according to part 1, h will be continuous because it is given to you that phi naught is continuous. Is this okay, class? Is this okay, class?
Yes, sir.
So straightforward using part 1, lastly by part 1, we have g dash t, or you can write g dash to be continuous on closed interval c comma t. Hence, g is continuously differentiable, right, class? On C. And this completes the proof. Is this okay, class?
Yes.
I hope you must have enjoyed the proof. A lot of mathematics.
Yes, sir.
And all basics of mathematics only. So let's stop over here. And tomorrow I shall start with an application of this result to solve an important integral, which we shall be uh, further using in one of our important results. So just give me a minute. I'm taking your attendance. Ashish, Mamta, are both of you clear about each and every step of today's proof?
Yes, sir.
Yes, sir.
Good. Okay, class. Thank you very much. Now we will connect tomorrow.